Hi, so for these notes, I'm going to go ahead and talk you guys through some of this stuff. We're going to do a little bit of review on reaction coordinate diagrams, Maxwell-Boltzmann distributions, and introduce something called the Arrhenius equation for this series. So for your collision model, you guys had learned about this in Chem or Honors Chem, and it talked about some requirements reactants need to fulfill in order for a chemical reaction to happen. So one, they have to collide, and we do know that when they collide, they have to be with correct orientation and with sufficient energy to force bonds to start to break so that they can form. And all the methods used to increase reaction rate, things like increasing temperature, increasing the surface area of your reactants, or increasing the concentration of your reactants, all work towards increasing the chances of collision and or increasing the amount of energy the reactants have. And all of that is to make sure that your reactants, that when they collide, they can overcome activation energy. And remember, that activation energy is the minimum amount of energy required to break those chemical bonds so that reaction can happen. One way to track the energy changes throughout the chemical reaction is a reaction coordinate diagram. So this is something that we've done before, so it should look very familiar to you. This one is for an exothermic process. A couple of things you guys want to be able to draw, obviously, is this shape for an exothermic reaction. Reaction progress is down on the bottom. Potential energy is your y-axis, and your activation energy always goes from your reactants up towards this activated complex. And that activated complex is where you have the actual collision of your two molecules, or that change is starting to happen. That is activation energy. For exothermic reaction, the energy released, or the enthalpy, is always found from the reactants and down to where the products are. So enthalpy for exothermic reaction should be a negative number, um, which means energy is released. A couple of things you guys just want to know, as I mentioned, you have the activated complex. That's whatever is present once you have that collision occur, if there is one. And sometimes you'll see it refer to the section as a transition state. The activation energy barrier just means activation energy. The other type of graph you do want to know is your reaction coordinate diagram for an endothermic reaction. So that looks something like this. So this is the decomposition of ozone down to oxygen and a free oxygen atom. Couple of things to know for that. Your activation energy is always from your reactants on up to where your activated complex exists, but your enthalpy is different. It's always from the products down to your reactants, this section. This signifies the amount of energy that was actually absorbed by the reaction in order to get this going. Very little energy is released in these endothermic reactions, which is why they feel cold. The sign for enthalpy will always be positive, which means you're going to add energy into this reaction to get it going. That's one diagram. The other diagram you guys need to be familiar again, you've seen this again, is the Maxwell-Boltzmann distribution. And what this tracks is the amount of molecules, so sometimes you'll see number of molecules or amount of molecules, and the energy that they have. And temperature can also be expressed down here. Essentially, temperature is energy. Activation energy will probably be a line at some point. That is your minimum energy to get the reaction going. And this graphs all of the energy that all of the molecules have, and any molecules passed to the right of the activation energy barrier, those are the molecules with sufficient energy to react. Obviously, this graph can change if you change certain characteristics. For example, if we increase the temperature from 300, we'll say for this graph, to 310, we'll see that all the molecules, they shift to the right. That's to signify that all the molecules have a little bit more energy. You'll see that more of the molecules are now pushed over the activation energy barrier, which means more reactants now have sufficient energy to react should they collide and when they collide. On the other hand, if you decrease the temperature, I couldn't surprise you guys with this one, but we can look on this side. You've got the activation energy barrier. The black line is supposed to represent normal temperature, but if we cool down the system, then the graph shifts to the left, which signifies that more molecules now have less energy to react. And you can see that the smaller section past the activation energy barrier right there, that just signifies fewer molecules are able to react. Okay, so those are a couple of graphs you saw at the beginning of the school year. These will come up again in this unit. And actually, from this Maxwell-Boltzmann distribution, um, some guy named Arrhenius derived the Arrhenius equation. The good news is you don't have to solve for anything regarding using this Arrhenius equation. You just have to make certain connections. This is defined right here. A is the frequency factor. This is how often those collisions would occur to result in an actual reaction. But again, you don't have to solve anything for that. You do have to know some couple of points. One of the things you do need to know is that as we increase activation energy, we know that the amount of molecules with sufficient energy to overcome the activation energy will decrease. We have to hold temperature constant. So you just have to be able to maybe look at this equation and interpret something like that. So what I did was I made AE, I just made it 5. And RT, I made it 2 for both. I kept those constant. Remember, temperature has to stay constant. And I just put in random numbers for activation energy, minus 100 to represent high activation energy, and then that 10 with the minus sign to represent lower activation energy. And I just solved for it, and you can see that with higher activation energy, your rate constant is very small, which means you have a very slow rate. With the smaller activation energy, your rate constant is significantly higher than this one, which means the reaction would occur faster than this one. The other thing you need to be able to do is to use this equation and explain how temperature would affect the reaction rate. So I did the same thing again, where I just made AE, I picked a random number 5, and then for activation energy, I just set it at 10. So you've got the negative 10 on top. And now I change temperature on the bottom. So the 40 is supposed to represent a higher temperature, and that 2 is supposed to represent a lower temperature. So you'll see with the 40, we get a higher rate constant than at the lower temperature, 2. So that makes sense. As we increase the temperature, we increase reaction rate, which means we have a higher rate constant. That is the lecture section for reaction coordinate diagrams, Maxwell-Boltzmann distribution, and what you need to know for the Arrhenius equation. Okay, if you have any questions, you can always email. Thank you.